Today's talk is a story, an argument, and an invitation. It sits at the crossroads of physics, philosophy, and the strangest thing we all carry around, the sense of being me. I'm going to tell you a story where a simple thought experiment about a perfect physical copy of your brain runs into philosophical trouble, and how a fundamental quantum rule might change the landscape. Let's begin. Imagine a machine, not a science fiction teleportation booth, but a machine that can, in principle, recreate every molecule in your brain, positions, momenta, chemical states, everything, and then assemble those molecules into a second brain somewhere else. The new brain is arranged exactly as yours was at a particular instant. It has the same memories, the same beliefs, the same quirks, the same jokes you tell yourself in the shower. It looks, acts, and reports just like you. Now ask yourself a simple gut question. If that machine runs, does the new brain have your self-consciousness? If yes, does it feel like you? Does your existing brain suddenly have another sense of self, being in two places at once? If no, then why not? That brain has every molecule exactly like yours, and may even be able to reconstruct your memory and personality. Why not the sense of self? This is not a parlor trick. Philosophers call it the duplication or fission problem, and it forces us to confront what we mean by personal identity. Is identity just a pattern of information and function, or is there something more than that? Some irreducible first-person fact that cannot be duplicated. At first glance, this looks like pure philosophy, but physics enters because the thought experiment depends on what counts as a perfect copy. If the world were purely classical and we could, in principle, measure and reproduce every microstate, then the duplication seems physically possible. If, however, the world is quantum at its core, then there are constraints on what can be copied. Those constraints might change what duplication even means. Enter the no-cloning theorem, a compact, rigorous statement from quantum mechanics. You cannot make a perfect copy of an arbitrary unknown quantum state. That sounds technical, but it has a poetic ring. It says there are kinds of information in the universe that refuse to be duplicated perfectly. If the thing that makes the self depends on such information, then maybe perfect duplication of the self is physically impossible. That's the rough idea I want to explore. Could the no-cloning theorem be the physical ingredient that prevents the paradox of two simultaneous selves, resulting from an exact copy of the brain? Let me explain the no-cloning theorem in plain language. In quantum mechanics, the state of a system, think of it as the full description of its quantum properties, is not like a classical list of positions and velocities. It can be thought of as represented by a vector in a mathematical space, and the rules for how these vectors evolve are linear. That linearity is beautiful and powerful, but it also has consequences. One of those consequences is this. Suppose you have an unknown quantum state, and you want to build a machine that takes that state and produces two identical copies of it. Quantum mechanics says no. There is no universal machine that, for every possible input state, will spit out two perfect copies. The proof is short and elegant and follows from the linearity I mentioned. Let me use a simple example to illustrate that. Imagine the universe is giving you a very strange challenge. You are handed a mysterious coin that is in three possible states. Either both sides heads, or both sides tails, or one side heads and one side tails. I know the coin with just heads and coin with just tails sounds strange, but because we are using classical objects, meaning coins, to mimic a quantum state, let's allow ourselves this little bit of weirdness. Your task is build a machine that makes an exact second coin in the same state. No matter what state the first coin is in, seems fair and easy. You build a machine so that if one coin with just heads goes in, two coins with just heads go out. If one coin with just tails goes in, then two coins with just tails go out. So far, so good. Nothing weird yet. But what if the coin with one side heads and one side tails goes into the machine? This is a superposition, a blend of possibilities. If you flip this coin many times, then half the time you will get heads, and half the time you will get tails. You might think this is simple. Just build the machine so that when two coins come out, each coin also has one side heads and one side tails. Exactly like the coin that goes in. And now, when you take the two coins that come out and flip them many times, you will have 25% chances of getting the combination of heads, heads, 25% chances of getting the combination of heads, tails, 25% chances of getting tails, heads, and 25% chances of getting tails, tails. After all, this is the definition of perfect copy or cloning. However, here is the key. Quantum mechanics says that any machine that works on a blend of heads and tails must also work on the heads and tails components separately and then combine them together. This is the rule of linearity. According to this rule, what will you get? The machine will have to copy the heads component to get a combination of heads, heads, and then copy the tails component to get a tails combination, and then combine the two outcomes together. The coins that come out are a linear combination of these two outcomes. If you flip them many times, you will get heads, heads half the time and tails, tails half the time. You will never get the combination of heads, tails, or tails, heads. This is different from a true cloning I mentioned above. The contradiction is baked into the structure of quantum theory. There is no way out. Why does this matter for our brain copy thought experiment? Because if the physical facts that ground consciousness include some arbitrary quantum states, then those facts cannot be perfectly duplicated. That would mean the duplication machine I imagined cannot, even in principle, create a perfect twin of self-consciousness. Importantly, this no-cloning theorem allows approximate cloning. You can make imperfect copies that are close but not exact. Maybe that's why, conceivably, an exact copy of your brain may have your memories and personality, but not your sense of self. Let me now lay out the chain of thought I find compelling, and then we'll test it from different angles. 1, classical intuition. If you could reproduce every molecule and its motion in another brain exactly, that brain would be a perfect copy and would have the same thoughts and memories, as well as the same sense of self. 2, the paradox. If a perfect copy exists, do you now have two selves? That seems paradoxical because your subjective experience is singular. 3, a possible escape. Maybe the reason you cannot have two selves is that perfect copying of the relevant substrate is physically impossible. 4, quantum ingredient. The no-cloning theorem forbids perfect copying of arbitrary quantum states. 5, hypothesis. Perhaps the sense of self depends on quantum states that cannot be copied. A duplicate could reproduce memories and behavior, but not the first-type person continuity from the original brain. That's the hypothesis in a nutshell. It's tidy, provocative, and it turns a metaphysical problem into an empirical one. Do brains host the kind of quantum states that matter for self-consciousness? Now, the sobering part, there is a heavy hurdle this hypothesis must clear. Brains are warm, wet, and noisy. Quantum coherence. The property that makes quantum states delicate and non-classical tends to vanish extremely quickly in such environments. When a quantum system interacts with its surroundings, it goes through decoherence, and its quantum weirdness goes away. Many physicists, including some who have thought deeply about quantum consciousness, argue that decoherence times in neural tissue are far too short for quantum states to play a sustained, causally relevant role in consciousness. But there are reasons not to dismiss the quantum route out of hand. Quantum biology has shown us that life sometimes exploits quantum effects in surprising ways. Photosynthetic complexes use coherent excitonic transport to move energy efficiently. Some birds appear to use quantum spin dynamics to sense Earth's magnetic field. These examples show that biology can, in special circumstances, harness quantum phenomena at physiological temperatures. If we assume that this hypothesis is plausible, then it offers a few advantages in solving the puzzle of copying self-consciousness. 1, it makes the duplication paradox physical. Instead of being a purely conceptual puzzle, the question of whether a duplicate feels the same sense of you becomes a question about what physics allows. If the relevant quantum states cannot be cloned, then the duplication scenario that generates the paradox is blocked at the physical level. 2, it separates behavior from first-type person continuity. A duplicate could be behaviorally indistinguishable. Same memories, same personality, same reports, yet lack the original subjective continuity because the underlying quantum substrate is different. That gives a principled reason why two identical-looking brains might not share a single eye. 3, it suggests new experiments. If consciousness depends on fragile quantum states, then disrupting those states should change subjective reports in ways classical models don't predict. That opens a path to empirical tests. It's an attractive move because it preserves the intuition that physical facts matter while acknowledging that not all physical facts are reproducible in the same way. That's all for tonight. As you step away from this little journey, let the idea settle for a moment that somewhere between physics and experience, between equations and awareness, there might be a boundary the universe itself refuses to let us cross.